Hello, everybody. So today what we're going to be looking at is section 3.2 in your book, which is Calculus of Vector Valued Functions. This topic is relatively straightforward, and I think you'll find it, less challenging than some of the other sections in the book. Um, Not the last lecture wasn't too bad either, but this one's about the same. Mostly, it's just going to come down to, do you know how to do derivatives and integrals, like you learned in, previous calculus classes? Nothing particularly challenging. So let's recall some stuff from the previous section. So we're going to be looking at um, vector valued functions. We're looking at vector valued functions like, for example, um, like R of t. They really like calling them R, and we know what they look like, right? It's just a function of a real variable and times an I plus another function of a real variable times j plus function of a real variable times k, right? And if you have two dimensions, right, then you just cross this one off the list, and then you've got a vector valued function in plane instead of space. So almost everything we do, or everything we do, is for three-dimensional and two-dimensional vectors, um, but mostly I'll just stick to three-dimensional vectors. Uh, so here we go. So that's what we're going to be talking about, and what we want is a definition of a derivative. So we had a limits last time, right? So we considered limits before of these functions in 3.1. And now we're going to expand that to the derivative, right? What we saw about limits was that if you wanted to do a limit as t approaches a variable of r of t, that what you would do is you just would do the limit as t approaches a of the first function times I plus the limit as t approaches a of the second function j, and then the limit as t approaches a of the third function times k, right? So we know that you just do limits term by term, basically. And so now what we're going to do is we're going to look at derivatives of these. Okay, so so the derivative of a vector valued function. So this is a definition. The derivative of a vector value function, r of t, is this. So we're going to use the same notation as derivatives in calculus 1, just like a prime. So r prime, and it's going to be a limit. And we'll say delta t goes to 0. Could have used an h, but the book uses delta t. R of t plus delta t minus r of t. That's a vector, over delta t. So there you go. So that's exactly the same definition from calculus 1, pretty much, right? So let's see. And that's, of course, provided the limit exists. Okay. And then we can just make a couple notes here. If r prime of t exists, then we say that r of t is differentiable, right? So same language as calculus 1, it's differentiable at t. If r prime of t exists in an open interval, also say AB like that and write it as open interval, then R is differentiable in AB, like that. And then for a closed interval, according to your book, they say this. So we just add if R of t, sorry, um, no, erase, sorry, erase. If these two things are true as well, oops, if R prime of A equals a limit, this is weird. No, this is badly written. This is badly written by the book, but I'm just going to write exactly what they write. So for R to be differentiable on a closed interval, AB like that, then the following limits must exist as well. So R prime of A equals limit as delta t goes to 0 from the right side, and then R A plus delta t minus R of A over delta t. And the other one is R prime of B equals a limit as delta t goes to 0 from the left, and then it's R B plus delta t minus R of B over delta t. And so basically what they're doing is they're saying to be differentiable on a closed interval. So like what they want is, so to be differentiable on, and if you look at like an interval here, you put like A there and you put B there, right? Then what they're saying is you don't care about anything outside of the interval. So this is not the real derivative, right? This is only taking a limit from the right hand side. So they're saying that you're looking for the limit to the right of B. And this one for B is you're looking for the limit as delta t approaches 0 from the left. So we're over here. So to the left of B. And I mean, it doesn't say to the left of B, it says to the left of 0 for delta t. But to the left of 0 for delta t means delta t is negative. And if delta t is negative, then B plus delta t is less than B. So you're to the left of B. So, I mean, I was kind of compressing that a little bit. But to the left of 0 also means you're to the left of B. And to the right of 0 here means you're to the right of A. So you're here. And so what they're saying is we're only looking at the one-sided derivatives at A and B. We don't care about two-sided limits at A and B, right? We only care about the one-sided limits at A and B. This is so like, for example, so this is like a one-dimensional example, so like a calculus 1 example, but like trying to think of one. Maybe I don't have a good example. Yeah, I don't have a good example. But like if you were looking at a curve, right? So imagine the curve did this, right? And let's say that this is 1 or 2, 3, 4, 5, 5, 6, 7, 7. Okay, so like this, for example, there is no curve to the left of 2 and there is no curve to the right of 7, right? But we still say it's differentiable. So like this, for example, is differentiable on 2 to 7, even though there's not a two-sided limit at 2 or 7. So no two-sided limit slash derivative at 2 or 7, right? So that's why they do it. So, I mean, don't think too hard about it. It's just it's a relaxing of the definition of the derivative to deal with the fact that you might have a curve just on a piece, and you still want to call this differentiable at 7, right? You wouldn't say it's not differentiable at 7 because there's no right-hand side. We just say, yeah, it's fine. Fine at 7, fine at 2. And that's what they're doing here with these definitions. Okay, so let's get a move on here. So what else can we say? Yeah, so we can say this too, just kind of a note. In, Calc 1, you know that the derivative of a function at a point is the instantaneous rate of change. Of the function. And if the function measures distance or position, distance or position as a function of time, the derivative is velocity, instantaneous velocity. Right? So that's something that you know, and it's still true, okay? This is still true for vector valued functions. So you can still interpret the derivative of a position as being a velocity. Okay, so I just wanted to make that point here, and then let's go ahead and we take a few derivatives. So these are not, there's no secret here because limits, and so here's kind of a thing you need to know, because limits are done term by term, or I'll say component by component. So are derivatives. So you don't have to, right? Just think about it, right? Like when we wrote that you have a vector valued function, and then when you do a limit of a vector valued function, you just do 3 separate limits, right? So when you're doing this derivative, which involves a limit of the r's, then that's still going to be 3 separate limits, one for x, one for y, one for z. So you're just going to do the derivatives that way, which means that you get to remember, you just get to take derivatives term by term using everything you know from Calculus 1. That is, derivatives are term by term. Just using the normal Calculus 1 rules. Now, be careful though. There are some specific ones for dealing with vectors in particular. So there's going to be more rules that we learn too, but this is just for like the basic examples here. So like if I have this, if I say find the derivative of, and we'll do a 2-dimensional one because they did a 2-dimensional one. 2t squared plus 3i plus 5t minus 6j, like that, you could use the limit-based definition of the derivative, but basically it would boil down to this. So don't do this, but you could say that r prime of t is the limit. I'm going to use h goes to 0 of r of t plus h minus r of t over h. But then that would be like the limit as h goes to 0 of, and then it would be like, if you call this f of t and you call this g of t, then it would be like f of t plus h minus f of t over h I, and then plus the limit as h goes to 0 of g of t plus h minus g of t over h, right? Because this limit would be done term by term. And then this right here, this is just going to be, well, this is the normal calculus 1 definition of the derivative for f. So this is simply f prime of t I plus g prime of t j, right? So you just do the derivative term by term. So in practice, you don't do that. You don't use that definition. You skip the definition and do this, right? So r prime of t is going to be, well, what's r? Let me just copy paste it. Duplicate. This is just to look at it. I'm going to erase it as soon as I've done this derivative. But you're simply going to do these derivatives term by term. So what's the derivative of 2t squared plus 3? Right? That's just 4t, right? I. And then you do your derivative of 5t minus 6, which is just 5j. So you just do your normal derivatives for each piece. And that's it. Right? So you would just jump from this top line to this line, and you don't actually need to write anything out with these limits here. Okay, so that's the key. So they write this as a theorem. They'd say if r of t equals, I'm looking where I wrote f of t, g of t, h of t, duplicate. I lost it that, but all right. So if that's your r, then r prime of t is f prime of t I plus g prime of t j plus h prime of t k. So that's what it boils down to, and that's from what we just did. I did a little bit. I wrote out the limit anyway, and there you go. So that's how you do derivatives. Again, if there's no third component, then there's no third component. So let's see here. Let's do one more example of this before we move on. Find r prime of t if r of t equals e to the t sine t I plus e to the t cosine tj. We're going to do two components here just because. Let's work. All right, so if you were going to do this, we know you just do it term by term. That basically r prime of t is going to be the derivative of this component, and then plus the derivative of this component. So I'm putting the primes on to indicate that I still have to do the derivative. And then you have to remember everything about derivatives from your Calculus 1 class, right? So this right here, you have to remember um, you do each of these, but each of these is going to need the product rule from Calculus 1, right? Because the e to the t sine t is a product. Okay, so you just do the product rule, right? So product rule is going to be the derivative of the first thing times the second plus the first thing times the derivative of the second, I. And then you're going to have same sort of thing, derivative of the first thing times the second plus e to the t, derivative of cosine j. Okay. So you have to do a product rule there twice, and then you actually have to take those derivatives. So what do we get? We get the derivative of e to the t is e to the t. So you get e to the t sine t plus e to the t, the derivative of sine t is cosine t, I. And then you've got here, same sort of thing. The derivative of e to the t is e to the t. So you have e to the t cosine t plus e to the t times the derivative of cosine, which is negative sine. So I'm going to change that sign. Didn't do a good job. J. Okay, so that's done. The point of that was you don't get to forget your chain rule, product rule, quotient rule, all those rules. Okay, so that's how you do those derivatives. Now what we're going to get is a list of special like vector valued rules. Okay, so these are going to be kind of rules for derivatives of vector valued functions. All right, so the setup is R and U are differentiable vector functions. All right, of t. F of t is differentiable. C is a scalar, which again is just a real number. Okay, so just everything has a name there. This isn't that hard to understand. The ones with vector symbols are vectors. F of t is a function, and C is going to be a constant. Okay, so pretty straightforward there, and these are the rules. So start out, don't like the way they use Roman numerals or whatever. So if you take the derivative of a constant times a vector valued function, the result is just going to be the constant times the vector valued function. So that's just how you expect it. But this rule needs to be stated because we never had this rule when this was a vector function before. So if we don't write it down, then the rule doesn't exist, right? So you got to write it down. So obviously that's for scalar multiples. Second rule is going to be just for sums, right? So we're just doing this as simply as we can. So we got R plus or minus U. And the result would be R prime, you take the derivative of the first vector valued function, plus U prime, you take the derivative of the second function. That's going to be sum and difference rules. Then what we get is going to be Three different product rules. Actually, hold on. One, two, three. Yeah, three. So three different product rules. So basically, you know the product rule. It's going to be the same product rule that you know, so don't stress. But you have one product rule for when this is a function of a single variable. So this is a real valued function. I mean, this is also a function of a single variable, but this is a real function, right? The output is a real number. This is a vector valued function, so the output is a vector. So this is a number, or this is a real number, and this is three real numbers potentially, right? So scalar and vector functions. And the product rule is exactly the normal product rule. So don't, you don't have to think super hard about it, right? Like this is f and r, so f prime r plus f r prime, right? Prime r plus f r prime. So that's just the regular old product rule, right? The only difference is that now there's a vector symbol. Okay, now what if we do a vector and a vector? What if I do the derivative of a vector times a vector? Now, if I do a vector times a vector, I'm actually tricking you. See if you can think about what the trick is. What's the trick here? Well, I'll show you the trick. The trick is, how do you multiply a vector by a vector? Right? Remember that there you can't just multiply a vector times a vector. There's two different ways that we have defined to do that, but they're different, right? You can't just write them next to each other. So the first one is a dot product between two vectors, and the other one is a cross product between two vectors. So each of those has its own product rule, and they're just the regular product rule, okay? But you just have to, the regular product rule, you just have to write it out with the right symbols here. The form is the same as the product rule, I should say. So like when you do this, it's going to be r prime dot u plus r dot u prime. So it just looks like the product rule, but this was a dot product, so these are dot products. Easy. And then we do the one for the cross product. So r of t cross r prime of t cross u plus r of t cross u prime. Okay, right? So it's just, they're all just the regular product rule with the primes in the same place. It's just that the type of multiplication is different between these three, right? This is scalar times a vector multiplication, so you can just write them next to each other. This is dot product multiplication. This is cross product multiplication. But the actual form of the rule is the same, which means that they're not that hard to remember. You just write out what the product rule probably should be, and you'll be right. All right, what's next? Well, what's next is chain rule. So if you have the derivative of a function in a function, right? So r takes, like, the variable of r is a single real number. So you use a function. If you're not going to use t, you can put t into a function, but the function must also return a real number, and then that can be plugged into r. So you can have r of f of t. You couldn't do r of u of t because u is a vector, and it doesn't make sense to plug a vector into a vector. That doesn't make sense. So this is what we got, and it's just a regular chain rule. You take the derivative of the outside function first, and then you multiply by the derivative of the inside function. So that's just the regular chain rule. They put a dot here when they write it. I just didn't, because then it makes it look like it's a dot product, but it's not a dot product, just regular multiplication. So that's just the chain rule. as we've known it. And then last rule, um, this I'm sure we're going to use to prove something later on, which is why they're showing you it. But let's say if r dot r is a constant, then r dot r prime equals 0. And so that's just like a rule that we're doing because apparently we need it. Okay, so let me see here. Yeah, so you can prove these, like any of these are very straightforward to prove. You're just use, basically you just use this and you can prove any of them. Just that rule for how to evaluate these. So like proofs are straightforward. Easy enough. Example, let's just prove 3, right? I was just trying to pick one that wasn't too easy, but also wasn't too hard. So if you're going to do the derivative of f of t times, I wrote r of t, I think, like that. Like, first of all, what's r, right? So let's let r be, well, we already used f, so let's just call it like g of t I plus h of t j, and let's not have a k component because there's less writing this way. So if you were going to do this derivative, right, then you would have, that would be the derivative of, if you multiply this f times this r, the f would get distributed on both components. So you would have f of t g of t I plus f of t h of t j, and we don't have a k component. Then you would take this derivative, but in order to take this derivative, you do it term by term, right? So you need this derivative and this derivative separately. So when you do this derivative, you'll use the product rule for real numbers, or for real functions. For scalar functions is how I should say that. Right? That's like calc 1 product rule at this point, because we're doing these derivatives separately. So you would get like f prime g plus f g prime, like that, plus, oh, and then that's I, and then plus, the other one would be f prime h plus f h prime, and that would be j. Then what you can do is you can, well, what are we trying to get to actually? So we're trying to make it look like, where is it? We're doing 3. So we're trying to make it look like this. So f times r, and then f prime r, f r prime. Okay, so we want to collect the f primes first. So if you collect your f prime terms, then you've got one f prime term here, you've got another f prime term here, right? So I could write it as, like, let's say we use 2 different colors here. So you could have f prime g plus f prime t h. Oops, wrote it wrong, sorry. So you'd have f prime f prime g of t, but then times, that's I. So you still have the I there. And then you've got f prime t h from over here times the j. So that's got a j. So group those together. And then you've got separately the other terms, which are f of t g prime and f of t h prime j, like that. And then what you can realize on these is that here they both have an f prime. So that's like f prime of t times g of t I plus h of t j. And let's just keep going. And this right here, g of ti, h of tj, that was the original r. So that's f prime of t r, right? Now, if we do this for the other one, same thing. These both have an f, so you factor out an f here. You've got g of t, g prime of t plus h prime of t, j. This should have a, oh no, it's fine. So you factor out the f, and then this right here, g prime, what? This is written wrong. Hold on here. I wrote this dumb. I wrote it bad up here a couple lines ago. Right? This has got, oops. So when we're doing this, right, this term is from here. So this term has an I on it, which I didn't write. And this term has J on it that I didn't write. So this one has, so where I was writing the J there doesn't make sense. So this was an I, and this is a J. Okay, sorry about that. Once you write it down wrong once, I just copy it forever. So look at this, G prime I H prime J. Well, that's just the derivative of the G and the derivative of the H, right? So if you take the derivative of the G and the derivative of the H, that's how you get R prime. So this is just R prime. So this is f of t R prime. And then that's done with the proof because this is the product rule that we have here. Okay, so it really boils down to just because we have the product rule for the scalar functions, it's just two separate product rules. And then when you're done with your two separate product rules, you write it so it looks like one product rule again. And if we had done this in 3 dimensions, there just would have been a third one to do, which would have been annoying, but we could have done it. I mean, there would not a third one here. There would have been a third component in here and a third component in here. Okay, so all of these proofs are basically the same. The one that you might say is different is number 7. We can do number 7 as well. 7 proof. Okay, so what is it? Oh yeah, so start with the left-hand side. R of t dot R of t equals a constant. So they're saying if this is true, then this is true. So we're trying to get here, but we don't know how yet. So what we got here is just this. Now, if we take the derivative of both sides, so apply d dt to both sides, so you have d dt of r dot r equals d dt of the constant. Now, on the right-hand side, that's the derivative of a constant, which of course we know is 0. Now, on the right side, you've got the derivative of a dot product. And you might say, oh, we don't know how to deal with that. But yes, we do, because we specifically had rule 4 here. So, I mean, you can't prove rule 7 until you prove rule 4. We didn't prove rule 4, we proved rule 3, but whatever. You can do rule 4 without too much trouble. So we just have product rule. Okay, so we're going to apply the product rule, which is true. So we're going to have r prime r plus r dot r prime. And the thing about these is because this is r and this is r, they're the same r, you end up with r prime dot r and r dot r prime, but you probably remember that the order doesn't matter here because dot products are commutative. So you can write this as r prime r plus r prime dot r. These are dot products. So you can write it that way. And then once you write it that way, they're really just two of the same term. So it's two. I just realized I wanted to write the r's first, so I'm changing the order. Sorry. So you have two of these things equal 0. But if you just divide both sides by 2, then you get r of t dot r prime of t equals 0. And so that completes the proof, although we didn't explain why anybody would care, right? So proof is done, but we never said why we care about this property. Still don't know why they bother listing it. So maybe we will learn in the future. But for now, we don't know. But we can prove it. So we did. So if r dot r is a constant, then r dot r prime is 0. So those are those. We can use the properties for, like, for example, and you do use these in other math classes, by the way. I should warn you, right? You do use these in, physics classes, engineering classes, like, fluid dynamics, more advanced differential equations classes. Not your first differential equations class, but later, etc. I still have flashbacks to fluid dynamics. It's terrible. But you do need to be able to do these rules on vectors. So it comes up, okay? So these aren't really things that you can just like forget once the class is over or something, right? So here's an example. So yeah, so example, just example. All right, like let r equal 6t plus 8i. You know what? I'm tired of ijk. I'm skipping it. I don't want ijk. 6t plus 8, 4t squared plus 2t minus 3, 5t. Let u be another vector, t squared minus 3, comma, 2t plus 4, comma, t cubed minus 3t. Okay, so we got two vectors. I think this color is bad, so I'm going to switch colors. And we want a compute hold on. Okay, I was trying to decide if we were going to do both of these. We are going to do A and B. All right, so d dt r of t dot u of t. Let's do that. See what we get. Okay, so what you would do is you have to just apply the property, right? Apply product rule. So don't jump to just doing this. Well, okay, you could just do the dot product first and then do the derivative. That's okay. But we could also apply the product rule first. So let's do that. So we could just do r dot u and then the derivative. But we're not because we're not. All right, so let's apply the product rule. So if we apply the product rule, you would have r prime dot u plus r dot u prime. Okay, so that's how we would write it. So we have the r prime and the u. We don't have, or sorry, we have the r and the u. We don't have the r prime and the u prime. So we have to calculate those. So what you would get, what's r prime? So r prime would be the derivative of r. So I'm just going to do this derivative. So the derivative of 6t plus 8 is just going to be 6. The derivative of 4t squared plus 2t minus 3, the derivative of 4t squared is going to be 8t, and then plus 2. And then the derivative of 5t is 5. So there's your r prime dot. U is the one that they're listing there. Just have to write it all out. Quite tedious. Move this over to give myself more room. Plus r. R is 6t plus 8, comma 4t squared plus 2t minus 3, 5t dot. Man, this is so much, really hard to fit it on the page here. Gotta do that. This is all one line. Dot u prime, that's the derivative of u. What's the derivative of u? So we got derivative. So the derivative of t squared minus 3 is 2t. The derivative of 2t is 2. And the derivative of t cubed minus 3t is 3t squared minus 3. Okay, and then after you do that, you can do this dot product. Now, so the dot products, right, are multiplying the components, right? So now do the dot product. So like you've got to, I'll do half of it here. Like you need to multiply this by this. You need to multiply this one by this one. You need to multiply the 5 by this. And add those together, right? So you got like the two yellow are the 6 t squared minus 3 plus, then you got 8t plus 2 times 2t plus 4. And then you got plus 5 times t cubed minus 3t. Then we got to do the same thing for this one down here. So 6t plus 8 times 2t is going to be 12t squared plus 16t, I think. Then we got to do this thing by 2, so double all those. Plus 8t squared plus, oh, I can't even read my own writing. Is that 2t? Yeah, 2t plus 4. That's 2. Wait, no. Yeah, 2t minus 3. Okay, that's 2t. Okay, so we're multiplying that by 2. So we got 2t times 2 is going to be plus 4t. And then you got minus 3 times 2 is minus 6. And then we got 5t times the 3t squared minus 3. So we got plus 15t cubed minus 15t. Wait. Yeah, 3t squared minus 3. Okay, so you get all that. And then you've got to add it all up, which I'm not going to do. I copied this from the book, so I'm just going to write the answer that's in the book. Okay. A lot of work. All right, but we could do it using the rule. So we did the product rule for the dot product, and then we did the derivative. It would have been a lot easier. I think, to do the dot products first, but you would at some point have to multiply like this by this and this by this, which is a lot of foiling stuff out. But still, I mean, we had a lot to write out anyway, so who's to say which is less work or more work? Okay. So now we want tangent vectors. So tangent and unit tangent. Okay. So it turns out that if you've got a curve, which I don't know. Okay. So in Calc 1, the derivative is like the slope, right? Okay. Um, in this case, where like the derivative of a vector gives you kind of three slopes, okay? And the result is that you actually get an interesting thing. So let me just draw a curve here. Oops. All right. So there's just a curve in space, right? And so like let's call this R of t. All right. Now, if you pick a particular point on a curve, right? Like that could be R of, I don't know, like t0, right? Just some um, someplace on the curve. Now, where is the derivative? How is the derivative related to this point? And so the way the derivative is related is if you find the derivative and you plot it at this point, the direction that it points is going to be tangent to the curve, like that. R prime of t is tangent to the curve. Okay. So like the three parts to the derivative are basically like the slope, like the x slope and the y slope and the z slope. And when you combine them, you get a direction vector that points in the same direction of the curve. A better way to think of it probably is this. So you know how I said that the derivative was a velocity, right? Well, velocity has a direction. And so the direction of velocity is the direction that you're traveling. Well, you're traveling tangent to your curve, right? You're traveling in the direction that you're traveling. So the velocity points, like when you're right here, you're heading this way on the curve. So your velocity points in that direction. So since r prime can be interpreted as a velocity, right, which has direction, it's not surprising that the direction of r prime is the direction that the curve was traveling, tangent. So it's not surprising that r prime points in the direction tangent to the curve because you were following the curve. So your velocity should be parallel to that. Okay. So it points that way. It actually points tangent. So um, what we say is in our definition here. So let's see, be a curve with equation. I'm just saying equation, but vector valued function r. Assume r prime t naught exists, right? Derivatives don't always exist, but if they do, a um, not a, I want to say, then r prime of t naught is a is tangent to the curve at the point r prime of t naught, and a unit tangent vector for c can be defined as, so they use uppercase T here, and it's r prime divided by the magnitude of r prime. And that's just because that's how you make a unit vector, right? Divide a vector by its length and it's a unit vector. So unit tangent vector can be defined this way. Okay, and that's provided that the denominator, prime, provided that the magnitude of r prime is not zero. Right, because you're still not allowed to divide by zero. So there you go. So yeah, how do you get a tangent vector? You do a derivative. Okay, so here's an example. Find, let's see, the unit tangent vector for, I'm going to go r of t, we're going to go cosine 3t, I plus sine of 3t, j. Okay, so this is a circle. Right, you should kind of remember that you should remember that cosine I plus sine j, right? That was how you parameterize a circle. And the 3 that we put in here just makes it go around 3 times as fast. But that doesn't matter. Like how many times it goes around, doesn't matter. So here's r. So if you want t, the unit tangent vector, you need to find r prime. So find r prime. Right? That's easy. That's a very straightforward derivative. No special rules required. So the derivative of cosine 3t is negative 3 sine 3t. Don't forget the chain rule, I. And then plus the derivative of sine 3t is 3 cosine 3t j. Like that. And so then your unit tangent vector. So this is tangent, but the length is not normally going to be 1. Okay, so like if you want the unit tangent, t of t, that's going to be this vector, negative 3 sine 3t, I, plus 3 cosine 3t, j, over the magnitude of that vector, j. And you actually have to work out that denominator, right? So, so we got t of t here. I'm going to write it this notation, negative 3 sine 3t, comma 3 cosine 3t, just to make it easier for me to write. And then when we do this magnitude, you have to, not erase it. You have to remember how to do the magnitude of a vector, right? X component squared plus Y component squared plus Z component squared. But we got negative 3 sine 3t squared plus 3 cosine 3t squared. So we got, what do we got? Negative 3 sine 3t, comma 3 cosine 3t over, square this here. So when you square this, it's going to become 9 sine squared 3t. The 3t is not squared because it's inside the sine. And then also 9 cosine squared 3t there. And actually, if you remember how your identities, right, you would know that sine squared plus cosine squared is 1. So, recall sine squared of anything plus cosine squared of anything equals 1. So if you put a 9 in front of both of them, then these are going to add up to 9. You have that. Of course, square root of 9 is 3. So what you end up with is negative 3 over 3 sine 3t, comma, 3 over 3 cosine 3t, or just negative sine 3t, comma, cosine 3t. Okay, so that's your unit tangent. And so if you check the length of this, the length would be 1, right? Because of the same identity. You'd have to check it if you weren't convinced, but that's what you get. Point is this is the answer to that question. This was how you can calculate that unit tangent. It's a function because you can calculate the unit tangent anywhere on this circle, right? So you could just like pick an angle and figure out that like the unit tangent looks like that. That would be like t of some t. I don't know what t, but it would point in that direction, right? But if you come over here, then the unit tangent points straight down, right? So they just point in a circle here in the direction of motion, or the direction that you would draw the curve is the direction that the unit tangent is going to be in. There's not really too much to say about that. Just like you can do this unit tangent thing if you need to. It becomes more important later in the class. Okay. So I want to quickly do, it's already an hour, so I want to quickly do indefinite integrals. Integrals works pretty much probably just like you expect. So I'm not really going to do anything here. So integrals of vector valued functions. All right. So, by the definition, if you're going to be doing, you can do indefinite integrals. If you do an integral of f of t I plus g of t j plus, I'm going to write it for 3, h of t k dt, how are you going to do that? You can probably guess. You just do 3 separate integrals. Integral of f I plus integral of g j plus the integral of h. Okay. Okay. So this is just how you're going to do it. You just do them term by term or component by component. Just like derivatives. All right. Now, how do you think definite integrals work? Same idea. So what I'm going to do is I'm going to copy all of that, duplicate it, bring it down here, and then I'm just going to pick a different color here and just say simply, if you have like an A and a B there, well, all of these are A and B, A and B, A and B. Okay, so that's just our definitions actually of these. So these are just how you integrate these types of functions. So basically you just have 3 integrals for 1. So everything's 3 times as much work, right? That's what you get. The only kind of thing that's a little bit tricky is the constants of integration, right? So let me write about that. Or the only thing that's potentially confusing, I think, the constant of integration, constant of integration. All right. So what does that mean? So like, suppose you have this. So let's say, suppose we integrate, let's say r of t, which equals f of t g of t. Now f of t I plus g of t j. So just two components, right? So let's say we have that. Um, you know that the integral of r, indefinite integral here, is going to be the integral of f of t uh, dt I plus the integral of g of t dt j, right? So you just do those integrals there. But so you find antiderivatives, right? You go find antiderivative. Do you know how to do integrals? Uh, I'm just going to call them f and g, capital F and G. That makes sense, right? So let's use different colors here, I think. So for the first one, right, you do this integral, you get capital F of t, but you just did an indefinite integral. That means there's a constant of integration. So there's like a plus a c, right? So you have that I. But then for the other one, you're going to do an integral. You're going to get, the antiderivative of g, but you're going to get another constant, right? And the thing is that there's no reason why this constant should actually be the same constant. So what you do is, all right, this is actually like a C1 and the other one is a C2, right? They don't have to be the same. So C1 and C2 aren't the same constant typically, don't have to be the same constant. All right. So the way you could do this is you could combine these together, right? So if I keep going here, I'll say the integral of r of t dt, you could write it this way. It would be the f of t, right? Capital F of t times the I, like that, plus the g of t j, right? G of t j. And then what about the constants? What you can do is you can stick the constants together. You can stick the constants together in a vector constant where the vector constant is the vector C1, C2. I'm mixing the notation again because I didn't feel like writing J. So if you're doing the integrals, right, like the integral of r, and you get, derivative of the first one, integral of the first one, antiderivative of the first one, I, antiderivative of the second one, J, plus a constant, just make sure you understand that your constant itself has I and J components because each one of these came with their own separate constant. Constant for the X component, constant for the Y component. Okay. Let's see here. Let's just do one integral. I'm not really going to do a lot of these because they're very straightforward. So we're just going to compute the integral from 1 to 3 of, hey, that's dumb. Parentheses 2t plus 4i plus parentheses 3t squared minus 4t j dt, right? And so what do you do here? Actually, something we didn't say, but I'll bring it back up here to look at it, is if you look at this formula here for the indefinite or for the definite integrals, keep in mind, right? You do this definite integral, you get a number. This one's a number, this one's a number. but it's the number times I, number times J, number times K. So your result here is not going to be a constant, it's a vector, right? Constant I, constant J, constant K. So it's a constant vector. So your result here is going to be a vector, just like this integral is going to be a vector. So we do expect a vector for an answer here because there's I and J components. So what we got is the integral from 1 to 3 of 2t plus 4 dt I, and then plus a separate integral 1 to 3, 3t squared minus 4t dt j. So you just split it up and then you just do each one separately and throw the I and the j on the end. So you would just do antiderivative. So you get antiderivative of 2t is t squared. Antiderivative of 4 is 4t. That goes from 1 to 3, and you're going to multiply by I at the end. This one, antiderivative of 3t squared is t cubed. Antiderivative of negative 4t is going to be, 2t squared. They give you nice, easy functions, I see. So we get that. We got to, substitute these in here. So we got to put in the 3 squared plus 4 times 3 minus 1 squared plus 4 times 1. I plus, put in the 3 here, 3 cubed minus 2 times 3 squared minus, put in the 1 cubed minus 2 times 1 squared. J. Got to work these out. So this is 9 plus 12 minus what? Let's just add these together as we go. This is 1 plus 4, right? When you put in a 1, so that's 5. So just minus 5i plus, work this out, 27. This is 3 squared. 3 squared is 9. 9 times 2 is 18. So this is 27 minus 18. So that is 9. So that is 9 minus, this is, if you put in a 1 here, 1, oops, I'm going to erase that on accident. This is 1 minus 2. 1 minus 2 is negative 1. So minus 1, it's going to be plus 1. J. And so what do we get? Well, we get 9 plus 12, which is 21. 21 minus 5 is 16. So we have 16i plus 10j. So you do the integral. Yeah, so you do the integral and we got an answer. Okay. So, yeah, that's how it goes. Let's do, I think we have to do one kind of, one with a constant just to do it. Sorry, just looking for one here. Okay, so let's just do an indefinite integral just to make sure we can deal with it notationally. So when you're doing this, you could formally separate it into 3 integrals. Formally separate it into 3 integrals like I did with this for 2. Or if you think they're easy, you can just do them by hand here, or you can do them all at once. So up to you. I'll separate them, but I feel like this was easy enough to do without this extra writing. So you just do these antiderivatives one by one. So what's the antiderivative of e to the t dt? Of course, it's just e to the t, right? So you have e to the t I. Here we got the antiderivative of sine t dt. Of course, the antiderivative of sine t is negative cosine. So we have negative cosine t j plus, here I have an integral of 1 over t plus 2 dt. You got to remember how to do that. That's going to be a natural log. Natural log absolute value t plus 2. Okay. So there's your antiderivatives, right? So we just have our three antiderivatives. And then you need to write your constant of integration. And that's why for the constant of integration, we know that it's a c, but it's a vector c. And, that's what I wanted to make sure we understood. So vector like C1, C2, C3, right? Each of the three, this, and this, each of the three has their own constant, but we just stick them all together at the end. Okay, so that's how you would do a definite or an indefinite integral. Really just relies on what you know about integrals from previous classes. Okay, I think that's it for this lecture. I'm gonna stop so I can record your next one. See you guys later.